My name is Wei Dai, and my background is cryptography. I was at Bain Capital Crypto, and now I'm helping out at Delendum. So today I'm going to be talking about, I guess, tentative name is Rust Circuit Composer, and it's kind of trying to sketch out what could build that's better than maybe what we have right now, and especially in terms of witness generation for Rust ZK proving backends. Okay, so let's get started. I'm sure some of you here are familiar with Circum, and let me kind of walk you through a very simple Circum component. Okay, so this Circum component is called inverse. It takes one input field element, and you will try to return one circuit wire that is the inverse of the input wire. Okay, so it declares the input, it declares the output, and it has this assignment operation, which says that this out wire is 1 divided by the input wire, and this operation does not actually generate any constraints. And the reason for that is inversion is very hard to compute, but easy to check. So it turns out if you can just check that in times out is 1 to ensure that in is out is the inverse of in, and so like the way to optimize this in the ZK circuit is that you actually compute the inverse not inside the circuit, but you compute it as a non-deterministic input, and then you constrain it to be the actual inverse. And so this type of computation that happens outside the circuit is actually crucial to make sophisticated optimizations, right? So in Daniel's talk, he mentioned that convolution is easily checked rather than computed. Okay. So that's how you express that in Circum. And a little bit more on the difference between constraint generation and witness generation, and the difference between them. So at compile time, so when you're given a Circum program, the values of these input signals or wires are not known, right? And the circuit structure is also not known. And what you want to give at the end is the actual circuit structure and how you wire these wires together, but also how you would derive some values of wires from other ones, right? And there's a notion of circuit runtime, meaning once you fix a circuit and once you have the input, how do I derive the value for all the wires so that I can get to proving, right? So back to the previous example, the output wire that's inverse of the input is derived during witness generation time. It's derived during runtime, right? And if you go back to this example, like the code actually happens in the same place. So semantically and logically speaking, these two pieces of code actually happens at 2 different times. So you have this constraint generation code, which is parsed and processed during compilation to like allocate the wires and wire them together so that they're properly constraints. But the witness generation code is actually run at a different time. Like during compilation, you actually just ignore it. Okay. So really, there's different things we want to happen here. So first, we have to have witness generation be separate, right? To allow different optimizations. And second, there's 2 notions of ergonomics here. One is we should be easily able to parse what is witness generation that does not generate a witness, right? So that's easy to audit circuits, and so easily able to parse. Okay, this is witness generation and this is constraint generation. And second, they should actually appear at the same place, right? So similar to Circum, you actually want them to be, you actually want to generate the witness and constrain them in the lines next to each other. Otherwise, this will generate huge headache for auditing. And moreover, like the syntax of generating witnesses and constraining them should be more extreme lines, right? You shouldn't have to write very, very special library calls to do this. And finally, efficiency, right? So runtime code is actually run in a standard execution environment like WASM or native. And circuit compilation, it is done once, right? So there's different efficiency requirements for the generated runtime code and at compile time. You can do any arbitrary optimization. And so let me give a kind of counter examples to why current libraries do not achieve these targets. So libraries like Noir and Socrates do not currently have separate witness generation. So you cannot say that I'm going to allocate a constraint and I'm going to compute it in some manner during winner generation time, but I'm not going to constrain it yet. That's not doable in these languages. And in terms of ergonomics, so for Halo 2, for example, it's really hard to parse what is winner generation code and what is constraint building code visually, well, I would say, right? And so there's also variations of Halo 2 that's used in Ziki EVM, where during winner generation, you're actually composing some type of expression that you will run in during winner generation time. But that's like a special library call syntax that you build these expressions. And finally, for efficiency, with the exception of Circom, I think most libraries, at least in Rust, you will have a single piece of code that gets run both for circuit compilation and winner generation. So during winner generation time, you're doing all this additional work to recompute what my circuit structure is, right? And moreover, that type of circuit compilation, figuring out circuit structure, is in some sense inherently single-threaded, right? While the winner generation, the circuit is actually massively parallelizable. Okay, so I think that the current way of building circuits in Rust and generating winner generation code, it's leaves something to be desired. So let me give a quick example of what state-of-the-art circuit builders look like. So this is a bit of a simplification, right? So we'll come back to the same example of computing the inverse. So on the left-hand side here, we'll have the kind of Halo 2 style circuit building. We'll allocate a wire, and we'll say that at runtime, we're going to set the value of wire B to be the inverse of wire A, okay? And then we're going to return the wire that we allocated. And so there's some actual winner constraint generation code that I've omitted here. So you can see here that it's just Rust code that you're looking at, and it's hard to see what is constraint building and what is winner generation. And the second style is in Plunky 2. So you have the same type of structure where you allocate a wire, but instead of now writing the code directly in Rust, you'll say, okay, so please at runtime compute the value of B as the inverse of value of A. But now it becomes this really, really kind of complicated way of saying I'm just computing the inverse of field elements and sending it to another variable, right? So, what can we do this better? So there's something that I hacked together within the last couple of weeks that does the following. You use kind of the magic of Rust quotes. So what's happening here? We still allocate the first variable, but there's this kind of runtime synthesis API that allows you to supply any arbitrary Rust code with this Rust module called or Rust crate called quote enabled, where you get access to the pre-allocated wires. So you can use A and B directly inside inside here to generate your code, right? So this piece of code is run at compile time, but this piece of code does not get run until winner generation time. And during winner generation time, the value of hashtag A and hashtag B effectively directly points to pre-allocated wire in memory. Okay, so this might be a little bit abstract. But let's kind of check the couple of, the three targets we talked about, right? So I think, to me, this looks like, it's very, very clear what is constraint generation. So anything that's pure Rust is constraint generation. And anything that goes into this runtime call, it's runtime winner generation code. Okay, and I now will show you something about efficiency in later slides. Okay, so let's go through kind of more examples here. So this is exactly the same type of circuit builder that, for instance, Axiom or Plunky 2 has. You simply have different functions that takes a mutable composer and different input wires, and that can then invoke other components arbitrarily. So here is an example where we simply have a simple loop, and we're invoking different components inside, right? So just to show that the fact that you have this kind of runtime code synthesis doesn't really change how you would use it as an end user, where that does not matter to you. Okay, so let me show a kind of more concrete example of how this compiles down to runtime Rust code. So here, instead of looking at inverse, let's look at multiplication, where we take 2 wires, and we're going to allocate an output wire, and then we're going to say that A multiplied by B is equal to C. And so here's what the gadget will look like. And so first, in the runtime generated Rust code, you have a global vector of all pre-allocated wires. So here the size is 150. So during compilation of the circuit, the library will figure out what is the actual global number of wires that I need to allocate, and generate this code to allocate the wires. And so I'm showing this code here because there's an additional function that allows you to access each location of the pre-allocated table. So you give it. There's a function that you give it a number, and gives you a mutable reference to a field element, right? So what this component compiles to in runtime is 2 closure functions that does the following. So it takes some intermediate values, or actually pointers to these intermediate values, and it takes in the input wire, reference to an input wire, and it simply goes to the table and writes these values, right? So it goes in the global table, it pulls in the value for A, it goes in the global table, pulls in the value for B, and then writes it to the destination, okay? And the reason why there's 2 versions of these functions here is that there's an edge case where actually if you want to multiply the same wire twice, right? So if A and B are the same, points to the same location, then actually the computational path is different. And the library kind of figured this out during circuit synthesis that, okay, there's 2 versions of this function being used, and I'm going to generate 2 different closures and figure out which one to use, depending on context. And then once you have this closure, then it's used in other closures, right? So every circuit component gets generated to this runtime code that is closure, and closure will invoke other components. All right, so I know this is a bit technical, but yeah, let me kind of zoom out a little bit of what is the idea with improving the ergonomics of Rust circuit building libraries. So I think one big question in this space is, why do we build DSLs versus libraries, or vice versa? And I actually think if you think about witness generation time, generating witness generation time code that's efficient, that is argument against ZK-DSLs, because if you want to generate code that's efficient in WASM or in native, you shouldn't just be tied to field elements, right? So now your ZK-DSL had to take care of witness generation that have different machine types. Now we are doing is effectively you are kind of reimagining or rebuilding standard like runtime environment language, right? And so so on the other flip side of that, if we don't build DSLs, what do? Right? How do we get kind of circum type experience and for more modern proof backends? Well, let's use Rust, right? Why? Because all the modern new proof systems are building Rust. Okay, so let's not build DSL, let's build in Rust. And now finally, like, why another library? And so if you look at the current picture of the ecosystem here, let me actually skip to here. If you look at the ecosystem, so for Halo 2, Plunky 2, and as I'm blanking out, there's other Rust-based proof systems. So for every single Rust-based proof system, the proof system part is actually, I would say, quite simple, right? So you have access to polynomials, and you have like the actual mathematical proof system. But to actually access that proof system in a usable manner, you actually had to provide APIs to build circuits. And each library actually have their own way of building circuits, right? So Halo 2 and Plunky 2 have different circuit builders. And so in this landscape, when you want to build a new backend, you kind of forced to build a new front end if it has slightly different characteristics. And the idea is really, can we actually have one common type of front end circuit builder that can be plugged into different backends, so that when you have a new backend that for example, is hyperplonk, you can simply plug this into the universal circuit builder, right? That's designed just for circuit building. So that's the idea with this proposal. And let me kind of just show you the really rough architecture of this thing. So, like I said, there's window generation time is written in Rust, and there's runtime code that's generated in Rust. So effectively, you program your circuit in a single Rust file, and it gets compiled down to a binary that you run, which then generates this runtime Rust file, and then it gets compiled down again, which then takes input for your circuits and then produces an output. Okay. I guess very last thing I will mention is, so what is the benefit of this? So oftentimes, window generation shouldn't be the bottleneck, right? But with hardware acceleration, oftentimes, if you don't optimize window generation, it could become the bottleneck. If you have a single-threaded window generation and accelerated proving in hardware or GPUs, it could become the bottleneck. So here, just to show that this framework actually generates runtime code that's really, really efficient. And so there's a quick benchmark against of one circuit that's written in this library and Circom. And compared to the standards WASM generator, it is 500 times faster. And compared to the C++ runtime generator, it is still 10 times faster. And this is without multi-threading enabled. So this basically means that window generation is not going to be a bottleneck. All right, so that is the end of my talk. And I'll take any questions.
So does your library have different ways to handle deterministic assignment and non-deterministic assignment? Or do you have to write sort of the parallel deterministic assignment in every case in the macro?
So deterministic assignments are, so like when you write a low-level gadget, you always have to say how to generate and how to constrain, I think. So like, when you write adds, multiply, all the low-level ones, there's basically no, so like there's one base library that just takes care of like how you would write any components, but that library does not actually give you any components, right? So as a library circuit or library builder for your backends, you have to say how do I make an add component, right? So you have to think how do I allocate my wires and how do I generate them at runtime, right? But when you use that component then abstract away effectively because it already takes care of how. So when you write the add component, you have to say I'm going to generate runtime code. But when you use the add components, then you don't need to specify it. So it's very flexible in terms of that.
So this is an exciting new API for doing witness generation, sort of inline, similar to how it was done in ArcWorks and like old Bellman. But I think like one question that comes to mind is that whenever there is code gen, it becomes hard to debug because one, like the IDEs are garbage in terms of like dealing with code gen, and two, like the end result that gets put in the file might be like slightly modified from what I originally wrote. And how are you thinking about the debugging story there from a developer experience standpoint?
Yeah, a great question. I think this is maybe like question for Rust experts. I'm not a Rust expert, and I think so. I use the code library, and it passes information off the source file. So when you, so what the runtime code takes in is actually is not directly just Rust code, but code that have associated information of like what is the source file location for that particular line, right? So you could pass that information to your generated Rust code. So I think there's there's actually things to be done to make this more user friendly for debugging, but currently it doesn't have any of that. You're just like a proof of concept prototype that built.
For the 100x and the 10x witness generation speed up, it's still a little bit counterintuitive to me. Like, why is that the case? For example, I don't see any inherent reasons that the ZK DSL cannot achieve that. Does that imply there are some like improvement space for the ZK DSL counterpart?
Yeah, definitely. I think ZK DSLs could be, as fast, right? You could just build ZK DSL that's like Rust, where you generate runtime code like this. But the problem is you're effectively rebuilding all that yourself, and if you generate Rust code, you inherit from the optimization done by the LLVM and Rust compiler, and the code gen for WASM and native, and different libraries that you can access at runtime. So I do think, I think you could build ZK-DSL, but the effort spent there, it's maybe better spent elsewhere. And for the performance, so I suspect the reason is like for Circom, they generate C++ code that actually that's actually an interpreter, whereas in this library, it pre-allocates all the wires, and there's a lot of actually optimizations that LLVM is doing. So instead of actually looping a single, it is looping through it in a single-threaded manner, but the locations are expanded in some sense.